Hey guys, today we're looking at 3.5, which is all about systems of nonlinear equations. So starting with box 1 here with some definitions and some solutions. As you would expect, a system of nonlinear equations is just that. It's a system of equations, so it's a system of multiple different equations that have the same variables, and those variables represent the same things in both or all of the equations in that system. But one or both of the equations, because we're going to be dealing with just two equation systems right now, either one or both of them are going to be nonlinear. And for us specifically this chapter, since we are focusing on quadratics, we're going to have at least one of those be a quadratic equation. Could be both of them are quadratic, so both parabolas, or it could be a linear equation and a parabola. So here we've got a couple of examples of different solutions. So how many solutions we can get. We know when we were solving a system of equations back in in Algebra 1 with two linear equations, it either was all real numbers, so infinitely many solutions where the lines overlapped each other, they were perfectly right on top of each other. They could have no solution where they don't intersect, or one solution where they intersect just once. Now, we do still technically have the possibility of infinitely many solutions, but really that's very, 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 very unlikely. And in fact, I don't even bother talking about it because we are not going to see that. Technically, it is possible, but for the most part, the ones that we deal with, we got three different possibilities. We could have no solution where they don't intersect at all. We've got one solution where they intersect exactly one spot, or most likely two solutions where they intersect twice. And that could be here. I've got the two different examples. These top three are a quadratic and a linear function. The bottom one are two quadratics. So those are just a couple of examples of what it could look like where we have one, none, or two solutions, so 0, 1, or 2. So we've got three different ways of solving our systems, just like before, are those same methods. We'll still see for possibilities. We'll solve by graphing, we'll solve using substitution, we'll solve using elimination. So when we solve by graphing, as you would expect, we're pretty much just going to graph both of these equations and then find the points where they intersect. So for this top one, I'll use blue for a quadratic one here. So here, for graphing that quadratic, that's in vertex form. That tells me my vertex is shifted to the right one and down 2. So right 1, down 2, that blue point right there, that's my vertex for that parabola. I don't have anything out in front here, no a value, which means I could just use my regular 1, 3, 5 shortcut. So up 1 over 1, up 1, 2, 3 over 1, up 1, 2, 3, 4, 5 over 1, and we get that nice, as close as we can to getting that nice smooth curve graphed right there. I'll switch over to red for my line. For this linear function, we've got y equals negative 2x minus 1. So if negative 1 is my y-intercept, hey, look at that. We already found a point where they overlap. If I go, my slope is negative 2, so that's down 2, right 1. I could go up 2 and left 1. I'll grab my ruler, line them up. Connect my dots, draw a nice straight line with arrows on the end. So we can see here, even though it looks close at intersecting at two different spots, it actually is just this single point right here that I'm going to circle in yellow. That point right there is where my two graphs overlap, which means that's the spot where my x and y values are solutions to both of my equations. So in this case, my answer would just be 0, negative 1. That's my only solution for this box 2 problem. Moving on over here to substitution. Substitution is, as usual, is my favorite method of solving. It's usually the most reliable and the easiest to get set up. With substitution, just like we had before, we're going to solve for one of my variables in one of my equations and plug that into the other equation. Because you're going to have a nonlinear system where you have an x squared, and in this case we actually have an x squared term, an x term, and a y term, it is much, much easier for us to solve for y in one of our equations and plug that into the other one. And that's always going to be the case. So what I'm going to do here, I'm going to actually solve for y in this bottom equation. So I'm going to subtract x on both sides. This bottom equation rearranged is y equals 4 minus x, or negative x minus 4, or negative x plus 4. Once I know that that's true, I know that's what y is equal. Sorry, let's try that again. This is what y is equal to, so I'm going to plug it in for y in my top equation, because I don't have an equation that just has x's involved. So if I switch over to red, doing that substitution, x squared plus x minus, and here I'm going to put parentheses just because it's going to be important when I subtract that whole thing. X squared plus x minus 4 plus x equals negative 1. And now you've got a quadratic equation that we can solve using whichever tool we need to from the first part of this chapter. So here, when I collect up my like terms, x squared plus 2x, I'm going to move this 1 over here as well, minus 3 equals 0. Because now I got my choice. I could do solve by factoring, I could do quadratic formula, I could complete the square if I wanted to. It's really up to you on how you want to go about doing that. This is easy enough to factor. Right, this is just regular old school two parenthesis factoring, because you've got just x squared as your lead coefficient. So I'm looking for two things that multiply together to get negative 3, but add up to positive 2, which of course is x plus 3, x minus 1. Moving along, I'm going to set each of those parentheses equal to 0 to solve, to get my two x values. So x plus 3 equals 0, x minus 1 equals 0, tells me my two x values are negative 3 and positive 1. Now, we're not done with my system, because remember, when we're solving a system, we have to make sure we plug it back into our equation to find those y values. Here, since we have two x values as solutions, we're going to have 2 points for my solution. So if I'm going to switch back to, we'll switch back to blue. It's up to you on which equation you want to plug back into. As always, I suggest plugging back into one of your original equations before you started doing any kind of manipulation or substitution, just in case you made a mistake somewhere along the way. So definitely my bottom original equation, x plus y equals 4, is going to be the easier one to do. So if I do that here, negative 3 plus y equals 4 gives me a y value of 7. 1 plus y equals 4 gives me a y value of 3. So that tells me my two solutions, I'm going to do it in green here, are negative 3 comma 7 and 1 comma 3. Because that, again, those x values paired up with those y values are my 2 points. So at both of those x and y values, I could plug those into either of my two equations, and it would make my equation true. All right, last one, elimination. Elimination, again, for those who are comfortable with it, can be very effective. The issue with our nonlinear system is that when you're doing elimination, you do still have your two choices on whether you eliminate your x value or you eliminate your y value. The issue becomes when with a nonlinear system, you have two different, usually, and in this case we have two different x terms in each of my two equations. So if you're going to do an elimination and try and eliminate your x's, you have to eliminate both the x squared and the x terms, which that just becomes way too difficult to try and manipulate it to get all four of those numbers to match up perfectly. So if you are going to do elimination, my suggestion is going to be to eliminate your y values. Because there's always going to be a single y value. We're never going to have multiple y values. It's always going to be those two things. And really, again, it kind of depends on how it's oriented. Here, obviously, because I'm using this as an example, it is set up nicely for elimination. Because remember, in elimination, we want to make sure for the variable we're trying to cancel out, we're trying to eliminate, we want the same coefficient, but one positive and one negative. So here, I've got a negative y and I've got a positive y. So if I added my equations up, going down, we'd end up with 3x squared minus 3x, my y's cancel out, equals negative 2. So that tells me my equation I'm actually trying to solve would be 3x squared minus 3x plus 2 equals 0. So from here, it's up to you on which form you want to do, which method you want to choose to solve. That's not. Let's see. Can't really do regular old school factoring. There's no GCF. So if you wanted to try and factor it, you would have to do Xbox factoring. So if we wanted to try and do that, I'll do that over here in red. So top of my x is my first times my last, which is 6. My middle is -3. So if I tried factoring that, I'm looking for things that multiply together to give me 6, but add up to -3, which 1 times 6, 2 times 3, none of those add up to 3. So this is actually not factorable, unfortunately. So that means we have to do quadratic formula. So in quadratic formula, here's my A, here's my B, here's my C. Right, A would be 3, B would be -3, C would be 2. So let's switch over to green here. X equals -b. So I guess x equals -b plus or minus the square root of b squared minus 4ac all over 2a for those who forgot. So if I plug that in with my numbers here, -3 would be a +3 plus or minus the square root of -3 squared minus 4 times a times c all over 2a. So then I'll just go through and keep simplifying. 3 plus or minus the square root of 9 minus 24. Right, 4 times 3 is 12, times 2 is 24, all over 6. So 3 plus or minus the square root of -15, all over 6. So if we want to try and keep simplifying this, 3 plus or minus I squared of 15 over 6, but 15 doesn't simplify. And really the important thing here with our systems, although we can do that step that I just showed you, this I in here, this negative, should tell you that there aren't any real solutions, meaning in this case, my two graphs do not intersect at all, ever. So once you hit that negative underneath your square root, then you know this is no real solution, because these do not intersect at all. All right. That's all I got for you guys. The homework, which is posted on Classroom, figured I'd make it fun the first time around here. We're not going to do a bookwork right away. We'll do 3.5 puzzle time that is posted on Classroom. If you guys have any questions, concerns, thoughts, or ideas, hopes, or dreams, as always, make sure you guys are reaching out and letting me know. And if I don't see you anytime soon, then have a fantastic day.